One bourbon, one scotch, and one bill. One bourbon, one scotch.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So I'm going to finish up this chapter about conjugation by talking about the consequences of conjugation. So conjugation influences widespread chemical reactivity, so this in turn tells us whether a molecule is reactive or inert. And this is based on stability, right? So this is not a surprise. It also influences molecular structure, is a molecule planar/flat, is bond rotation hindered, and you saw this in the case of comparing cis versus trans. The molecular structure also affects the stability. Also, the physical properties of different materials is affected by conjugation. One thing that I'll talk about in this part is going to be color. And there's a lot of other different things that conjugation influences, but these are the three very important things you should know for this course. And so I'm going to start talking about the first consequence of conjugation, which is that the more extensive the conjugation, this leads to greater stability. So this makes sense because of all the things we've talked about in this chapter, right? But this also influences the distribution of products in a chemical reaction. Remember when we were looking at K equilibrium, if it's greater than 1, it means that the reaction is shifting more towards the products. And so consequence number 1 influences distribution of products in a chemical reaction. So this kind of covers this first point that we talked about. And also remember, this involves the equilibrium constant. And so for the reaction products, if you increase the stability, more of that product will be produced. And as an example, I drew out this particular reaction for you. So we start out with this particular molecule, we get rid of the water, and we end up with these two isomers. And what if someone asked you which isomer is going to be more prominent as the product when this undergoes this reaction? Well, let's look at it in terms of conjugation. If you look at this molecule right here, it has 2, 4, 6, 8, 10 conjugated p orbitals, because there's 2 p orbitals overlapping here, here, and here. This is a conjugated benzene molecule because you have pi, sigma, pi, etc. We also have another 2 conjugated p orbitals right here for the carbonyl group, the carbon double bonded to oxygen, and also for this carbon-carbon double bond. The reason being we have pi, sigma, pi. And so in this case we have 2 p orbitals right here, 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 and here that are all conjugated. On the other hand, if we look at this particular molecule, these 2 bonds right here are not considered conjugated because they're not alternating the pi, sigma, and pi. And so in this case, the only conjugated part of the molecule is this benzene. So we have 2, 4, 6 p orbitals that are conjugated. So in this particular problem, if someone asked you which is the more likely or which product will be produced more, it will most likely be this guy. The reason for that being that the more conjugation you have, the greater the stability. The greater the stability, the more product is produced. So now moving on to the second consequence of conjugation, It's the partial pi bond character. And this leads to a couple of things such as resistance to conformational change. And this is also indicative of the barrier to rotation. And this also causes planarity of atoms in the conjugated p orbitals. So as an example, I drew out the amide linkage between two amino acids in a protein. And this both coexist. But in this case, there's less torsional strain and you can rotate around this axis. So we have less strain and it's more stable. On the other hand, if the amine group right here is not in the same plane as the R group, in this case you have more torsional strain and it's less stable. And the resonance hybrid for the amide bond is shown right here. And this is extremely important for protein function, and so the barrier to rotation and planarity is critical when we talk about proteins. If you look at this example with glycine, serine, and valine as 3 amino acids making this peptide, you can see that the peptide bonds are in this particular conformation where the C double bond O is facing up and then the NH is facing down as shown right here. On the other hand, if the peptide bond was in this direction, this is less stable because of the fact that it's no longer planar and there's a barrier to rotation because of the torsional strain. All of the big actual bulky groups, like the R groups, are going to get on top of one another and it's going to cause more strain than when it's planar, like so. And so another consequence of conjugation is this partial pi bond character, which resists conformational change, which is the barrier to rotation. And finally, consequence number 3 says that highly conjugated molecules may be colored. And this also overlaps with the physical properties that I initially talked about. So examples of this is chlorophyll, which you find in the leaves of plants, right? And that appears green. Also, beta-carotene is a molecule you find in carrots. Also, lycopene is a chemical found in tomatoes. So all of these different molecules are colored as a result of conjugation. And so the origin of color comes from some portion of visible white light in the spectrum being absorbed, and the brain perceives the remaining light as color. So how does molecular structure actually control the energy of the photons that are being observed? Well, we can look at this particular diagram, which has energy on this axis, and we can compare a molecule with only single bonds, with a molecule with a few double bonds, and finally, a molecule with many conjugated double bonds. And so, molecular structure controls the energy of photons absorbed based upon how a molecule absorbs a particular photon and how an electron is excited to a higher energy molecular orbital. And the energy of the photon absorbed must equal the HOMO/LUMO orbital energy difference as indicated by this arrow right here. So this is going to be the LUMO, the lowest unoccupied molecular orbital, and this is going to be the HOMO, or the highest occupied molecular orbital. And this is the delta E between the two. So as you can see, the large energy gap for molecules with only single bonds means the transitions are likely to be in the UV region. And the UV region is right here, which is before the visible region. For a molecule with a few double bonds, the energy gap becomes smaller, but this region is still in the UV or the visible region. Finally, when we get to molecules with many conjugated double bonds, this gap is so much smaller. So this very small energy gap is likely in this visible region, which results in all of the different colored molecules. And so when you increase the number of conjugated orbitals, you decrease the delta E, or the difference in energy between the LUMO and the HOMO orbitals. And then when the delta E is low enough, photons of visible light are absorbed. And the non-absorbed portion of visible light spectrum is perceived as color.